Okay, thanks a lot, Pandu Rangan. It's a real pleasure to be here. So a few explanations about the contents of this two-part talk. First, the title refers to zero-knowledge proofs, but actually almost everything I say will equally refer to two different variations. First of all, sometimes we also consider proofs that are succinct but not zero knowledge. Almost always they can be made zero knowledge, but almost everything I say in this talk applies to this version as well. And also, I will interchange proofs and arguments. You heard from Manoj about arguments, which is a computationally sound version of proofs, also in Kermit's talk. So the term zero knowledge proofs will be used in a broad way. So a bit about this talk. I guess that you can crudely classify research on zero knowledge into two kinds. There is the theory-oriented or foundational research where we only care about crude efficiency measures, and the main goal is to minimize the underlying intractability assumptions. And then there is the more applied or blockchain-related part, where we're often willing to make very strong assumptions, sometimes just heuristics or security against best known attacks. And the goal is to push concrete efficiency to an extreme, say, get proofs that are 1,000 bits long. And this talk is actually some combination, and I guess that maybe what I'm saying is more relevant to the applied type of research or kind of puts it on a more systematic grounds and less relevant to the question of minimizing assumptions in zero knowledge, especially in efficient zero knowledge. Okay, and again, a general disclaimer is that please ask me questions at any time. Okay, so as you might have realized, zero knowledge in the last couple of years has become a real party. We've already heard in this workshop about quite a few exciting applications, many related to blockchain. It's been deployed. These applications also motivate new questions that didn't occur to us or new efficiency goals, and these new questions generate new ideas that in turn feed the excitement. So we have all this really a lot going on in this field in the last years. And these are just some of the buzzwords that represent actual systems that have been implemented. Some have been mentioned, and possibly Chaya will mention also tomorrow, these or others. And, you know, like every big party, an almost inevitable consequence of a big party is a big mess. So the goal of this talk is to try to partially clean this mess, or more accurately, make room for a new kind of mess. And specifically, what I will be presenting and advocating in this talk is a specific modular approach. There are different kinds of modularity, a specific modular approach for the design of proof systems. This approach is already practiced to some extent, but I believe that it can be practiced more often and more systematically than it currently is. And really the punchline is to maximize the separation between the information-theoretic component and the cryptographic component. This is really the punchline. And more concretely, we will discuss two kinds of general compilers. One is a cryptographic compiler that takes an information-theoretic, or if you want, a combinatorial object, and converts it into an actual cryptographic proof system that you can run. So this type of compiler uses crypto. And a second kind of compiler is an information-theoretic compiler that converts one kind of information-theoretic proof system into another. Okay, so this is the brief summary of what you'll see in the next couple of hours. Okay, let me be a bit more specific. So the setup is a standard setup for proof systems. We have some NP relation R. Here, X is a statement. Think of it as a theorem, or some encrypted value. And W is a secret witness held by the prover. And the goal is to design a zero-knowledge proof or argument system in the way that Manoj and Kermit defined. So it's possibly interactive or non-interactive, interaction between a prover and a verifier, in the end of which the verifier is either convinced or rejects in case he doesn't believe the prover. Okay, so that's our goal. And the typical step towards this goal is to convert this NP language or the statement that we want to prove into some intermediate zero-knowledge friendly representation. You can think of this as a computational model that is tailored towards efficient zero-knowledge. Coming from the theory side, you may stop here. You can say, okay, every polynomial time R can be represented by polynomial-sized Boolean circuit. But typically, when we care about efficiency, we move to more powerful computational models, such as arithmetic circuits that can perform addition and multiplications over a finite field, a RAM model that allows random access to the data. And these three purple representation classes, representation models, are ones that are specifically designed towards zero knowledge. So R1CS, rank 1 constraint satisfaction system, you can think of it as some convenient way of expressing arithmetic circuits where additions are for free. Tiny RAM is a specific kind of RAM model that is tailored towards efficient zero knowledge. And the quadratic span program, quadratic arithmetic program, etc., are models you will hear more about from Chaya tomorrow. Okay, so these are just examples for convenient representation models towards the design of efficient zero knowledge. Now, normally this is pretty much where modularity ends. So you convert your statement or what you want to prove into a zero knowledge friendly representation, and then you throw all the tricks you know to get an efficient zero knowledge proof. And here we will introduce this intermediate step, which is an information-theoretic proof system that I will refer to as a zero-knowledge PCP, PCP for probabilistically checkable proof. It's different from the traditional, it's broader than the traditional notion of PCP that you know, and much of my talk will be about different kinds of information-theoretic proof systems. What makes the proof system information-theoretic is that all of its properties hold with respect to computationally unbounded parties. So soundness holds with respect to unbounded prover and zero knowledge with respect to unbounded verifier. Why don't we use them in the real world? Because these systems are cast in some idealized model that assumes independence that we cannot enforce information theoretically. We need a crypto compiler. Okay, so you have different kinds of these. These will extend. You have crypto compilers that enable us to switch from these ideal models to something we can actually run without any idealized assumptions, just prover and verifier. Okay, so that's a general template. Here, for the crypto compiler, we need to either rely on concrete cryptographic assumptions, or very often in a practical context, we switch to generic models such as the random oracle model or a generic group model, which kind of make a leap of faith that you can treat the underlying cryptographic primitive as a random function. So it's a different, it's not like we still need, it's still a crypto compiler because the resulting proof, even in the idealized model, either soundness or zero knowledge will need to be computational, so the number of accesses to this ideal object will still be restricted. Okay, and again, this is a more accurate picture. Many different kinds of proof systems and many different kinds of crypto compilers, and I guess the question is why we need so many. Okay, and let me also say that this is where information-theoretic compilers fit in the picture. These are just, okay, so the information-theoretic compilers, I already said, and what Karmit talked about yesterday is a specific kind of information-theoretic compiler. This was part of Karmit's talk, which allows us to take information-theoretic MPC protocols and convert them into a certain kind of zero-knowledge PCP that I will describe in this talk. Good, so why do we need this modular design? First of all, there are generic answers that apply in every context. So in general, in science and engineering, why do we need a modular design? It makes our life simpler in several ways. It allows us to break a complex task into simpler building blocks. We can then analyze and optimize each of these building blocks separately. And we have potential for proving lower bounds. This is actually something that is quite unique in this context. We cannot really hope, cryptographic objects are very complex. They are inherently tied to computation. We don't have good techniques for proving lower bounds on general computations, on cryptographic primitives. However, if we look at the information-theoretic component, this is something that, at least in simple cases, we can hope to prove lower bounds. And in many cases, attempts to prove lower bounds on simple objects and failure to prove lower bounds leads to a discovery of better upper bounds. This is something that anyone who has worked on lower bounds, simple models of information-theoretic MPC, for instance, round complexity, right? Sometimes you fail, you get stuck, and understanding why you get stuck leads to better upper bound. So I believe that you also have examples in this domain, but whenever you have a simple enough object that you can try to prove lower bounds, this is also beneficial for upper bounds. Okay, there is a generality aspect. This is also something that we heard about from Karmit yesterday. When you have something that uses modular components in a black box way, you can hope to apply it in many different settings. You can take a code or hardware implementation of the information-theoretic part and then apply it in a different context with a different crypto compiler. Okay, so this also means that we have less papers to read and write, because if you mix the two components, you can write a separate paper or read a separate paper for each combination of each component. These things sometimes happen inevitably. People rediscover the same kind of tricks, and when they mix the crypto in the information theory part, it leads to, I would say, a bigger space of designs than if you break them into separate components. And finally, I already alluded to this in the lower bound part, but having this more systematic understanding of the design space leads us to better optimizations. So we can mix and match different components, different kinds of information-theoretic proof systems with different compilers. We'll see why this is useful. We can systematically explore the design space, right? We have a good picture of different options for each component. And we can port efficiency improvements from one model to the other. You'll see many different settings for proof systems. And in many cases, progress on one front takes a lot of time to propagate to the other fronts. So this modularity allows us to port efficiency improvements in an automatic way. Okay, so let me give a slightly more elaborate version of something that Karmit included in her talk, and this will also motivate the modularity and the systematic part of this study. This is really, if you ignore the type of assumptions that are being used and just focus on the conclusions, on the type of properties you may want to have in zero-knowledge proof systems, you have different kinds of features that sometimes conflict with each other. You can ask the following questions. Do we want an interactive protocol? Do we want a non-interactive protocol, or are we okay with interaction between the prover and the verifier? Is succinctness important, communication? Or maybe we have a very fast network or even smart card interacting with the reader where it's mainly about computation. How important is it to make the verifier work less than the prover? Do we want verification to be public? This is the case typically in blockchain applications, or maybe I'm authenticating myself or I'm proving to somebody specific who has some secret key or secret information. Right? There's a big difference between what we know in the public verification setting and in the designated verifier setting. Do we have a public input, or maybe the input is encrypted, committed, split between different parties? Are we referring to NP statements? This is almost always the case for zero-knowledge proofs. Sometimes we care about scalability, so this makes sense also for polynomial time statements. What about trusted setup? A big deal. Again, you'll hear about it from Chaya tomorrow. What about the type of crypto we employ, right? Forget about assumptions, but just in terms of structures, do we want to use, are we okay with using public key crypto, or do we want to use only symmetric crypto or hash functions? Do we want post-quantum security, or are we skeptical about quantum computers? Or maybe we're okay with quantum computers not existing today, that's good enough for the soundness. Okay, so all these are different types of considerations that, as I say, sometimes conflict with each other. And on top of them, you can pair them with quantitative aspects, right? Communication, right? So for each of these, even if you pick your answer to each of the previous questions, you could still try to optimize different things. You can try to optimize communication, prover complexity, and verifier complexity. And again, sometimes these optimization goals are in odds with each other. Okay, so the topic of zero-knowledge proofs or efficient zero-knowledge proofs is currently subject to commercialization efforts. There is a standardization process. There is a, already now in April, there will be the third zero-knowledge proofs conference towards standardization of zero-knowledge proofs. And also in this talk, zero-knowledge proofs play, in this workshop, zero-knowledge proofs play a prominent role. So maybe, if we work more, we just find a zero-knowledge protocol that will satisfy all of the properties we want. Okay, does this sound reasonable? Okay, so you could already infer from the way I describe things that this is not really a well-defined goal, but I want to give you, somehow tease you with an example that illustrates to what extent we have different optimization goals. So even if you give a detailed answer to all these questions, there is still more to be specified. So let me give you an extreme example, which is also kind of an unexpected use of proof systems in my own research. So suppose, you're given a choice between two different proof systems that have the exact same features except for one small difference. In the first system, the verifier needs to apply, now I'm talking about the verifier's computation. Let's say that it needs to apply a single application of a hash function, a common hash function, the one that is used trillions and trillions of times per second in blockchain applications. And a second type of proof system requires the verifier to perform a public key decryption, okay, in some public key crypto system. Which would you choose, right? I don't know, if you multiply it by 1 billion, clearly the first one can still run pretty fast and the second one will not terminate, right? So it seems like the answer is obvious that the first one is better. However, it turns out that for specific applications, the second one is actually much better. And the story is that, this is a story of a joint work with Dan Bonnet, Amit Sahai, and David Wu. And the story is that we were thinking about ways to make a general purpose obfuscation faster. So Manoj presented it as science fiction, and indeed, at this point, it's pretty much science fiction in the sense that we still don't have implementable general purpose obfuscation schemes. This is orthogonal to our limited understanding of their security. And a potential approach for building obfuscation schemes is to bootstrap using proof systems. So instead, say that I have a program that I want to obfuscate. Instead, I will publish a fully homomorphic encryption of the program that everybody can run in an encrypted way so that you can get an encrypted output. And then I will only obfuscate, think of a small trusted hardware that what it does is performs the decryption. Is this enough? Just to obfuscate something that decrypts a fully homomorphic encryption? This is not enough because this allows you to modify the program and run a different program, right? Obfuscation should only allow you to run the program that is being obfuscated, right? So you also need this small piece of hardware that is implemented via obfuscation to verify a proof that indeed the output ciphertext was formed correctly. So this proof needs to be verified very efficiently, but the usual metrics of efficiency do not apply. The relevant metric of efficiency here is obfuscation friendliness. And at least for current obfuscation constructions, the relevant metric is the size of a branching program. A branching program is a very different computational model, and it turns out that if you look at lattice-based encryption schemes, they have very small branching program decryption algorithm, and this leads to relatively efficient obfuscation. So I cannot say that this, so then this motivated us to look for lattice-based designated verifiers, SNARKs, which are sufficient for these purposes. And these are also motivated by other applications such as fast proving time and post-quantum security. Okay, so the lesson here is that when we talk about efficiency, we usually have one notion of efficiency in mind. We say A is more efficient than B. But in reality, you have many different application scenarios, more than we can imagine today. And even some of the current ones and certainly future ones will motivate very different efficiency goals than those we have in mind. So the lesson is that we should try to have a clean and broad understanding of the different techniques we have for the design of such proof systems. And even those that might look inferior can turn out to have attractive features that are useful for applications we cannot think about today. Okay, so that's a broad lesson. Just to give you one more example, you can think of distributing, yes? Yes, so there are two types of problems. Both are there is progress, and I think that the future is bright. But indeed, the traditional form of criticism against this line of research, it started in 2013 with the breakthrough construction of Gargetal that gave the first plausible candidate for general purpose obfuscation. And there has been some cycle of attacks and fixes. However, these attacks, they almost entirely affected an underlying assumption that was only useful for the proof of security. So if you look at the actual constructions, even the original ones, they were not affected in a major way. And by now, we have better, so there are very active lines of research on basing obfuscation on more traditional looking assumptions, and also coming up with new candidates, new heuristic candidates for obfuscation schemes. So my belief is that obfuscation is here to stay, and a very different challenge, which is totally orthogonal, is coming up with an implementable or concretely efficient obfuscation scheme, and this is only relevant to this second challenge. Exactly, to the existing, yeah, but I think that by now we have maybe 3 different approaches to obfuscation, and they all rely on branching programs. So certainly this is the dominant measure with respect to existing obfuscation candidates. Yes, and this other comment just gives us another type of efficiency consideration. If you want to distribute the prover between multiple parties, then again, whatever you think of as being efficient might not be the same. The metric is very different if you consider MPC friendliness. So you have these advanced cryptographic primitives of obfuscation, fully homomorphic encryption, MPC. They all motivate, or different kinds of MPC. Each of them has attached to it a different efficiency metric, which just further motivates this goal of diversification and a cleaner understanding of the space of possible designs. Okay, so back to the 20th century. So now, this was kind of looking into the future. Now we're looking back 20 years or so, not 20, but 40 years, 35 years to be more precise. So in '86, we had this seminal feasibility result that showed that if you have a bit commitment scheme, so go back to yesterday in my notes talk, he described this notion of a bit commitment and sketched the construction of Goldreich, Micali, and Wigderson of zero-knowledge proofs for all of NP given a bit commitment scheme. What can we base a bit commitment on? So in Manoj's talk for simplification, he used the random oracle to describe it, but it turns out that we know the minimal assumption, so the existence of a one-way function, a function that's easy to compute but hard to invert, is necessary and sufficient for building a commitment scheme, and therefore it suffices for general purpose zero knowledge. And finally, we also know some almost tight converse. So non-trivial general zero knowledge also implies a form of a one-way function. So this seems to settle, at least from a feasibility perspective, the big questions about zero knowledge. We know the assumptions that are necessary and sufficient for the existence of general purpose zero knowledge proofs. So why aren't we done? Well, again, the main reason why research on zero knowledge continued, at least in this community, is efficiency, but there are also many theoretical questions that are not settled by this line of research. Okay, so I will mention a few next. And to motivate what is coming up, I would like to recall to give a slower version of something that also Manoj explained in his talk, and this is the proof of this GMW result on the existence of zero-knowledge proofs for NP. So the construction applies to a specific problem, namely the three-coloring problem. You're given an undirected graph, and the question is whether the graph is three-colorable. Namely, the prover wants to prove that there is a way to color the nodes of the graph by three colors such that every two adjacent nodes have distinct colors. And this problem is well known to be NP-complete. So if we have a zero-knowledge proof for this language, then we can obtain a zero-knowledge proof for every NP language by locally applying. The prover and the verifier will apply the NP reduction. Good, so how does the proof work? This is what the prover can see. X, the statement here, is a graph. W, the witness, is a coloring of this graph. The first step is to apply this random shuffling of the colors. Okay, this is what the prover does. Just recolors the graph in a random way. There are 6 different possibilities. Okay, this is the shuffled coloring. Now the prover separately sends a commitment to the color of each node to the verifier. So you can think of this as each node has a color that is being sent to the verifier, but inside some envelope or a locked box for which the prover has the key. What's coming up? The verifier challenges the prover to open. The verifier picks a random edge in the graph and tells the prover, hey, please open the colors of these two nodes. The prover has to comply, otherwise the verifier rejects. And now the verifier checks that indeed these are colored by different colors. Okay, so note that this is, at least if you assume the commitments to be ideal, we have perfect zero knowledge because what the verifier can see can be simulated by picking a pair of random and distinct colors. Okay, the issue here is that soundness is not that great because the prover can cheat in a way that will make the verifier catch him only if a specific edge is opened. So this means that the prover can get away with cheating except with 1 over the number of edges probability. So to get around it, we repeat this protocol sequentially at least as many times as the number of edges. And then we know that we get constant soundness, and we can further amplify it to exponentially small soundness error by further repetition. Okay, so this is great. It's really wonderful. But there are several issues. To be more precise, 2 issues with this protocol. First, even though, as described, it seems very simple, proving security when you instantiate these ideal commitments by real commitments is more subtle than it seems. So if you go to Goldreich's textbook, this is at least 2 pages of technical things, including rewinding and some subtle probabilistic analysis. So if you want to prove the security, again, not in an ideal model, but using actual crypto primitives, this is challenging. And now, what do you do if instead of using, you have different versions of zero-knowledge proofs that are similar. If instead of using three-colorability, you use a different NP-complete language like graph Hamiltonicity, do you need to repeat the same proof, the same 2 pages? Okay, the other issue is efficiency. So we have 2 different sources of inefficiency. One is the carp reduction, right? So this is an NP-complete language, but now if you want to convert your statement or your language into this language, you still have a very expensive reduction. And perhaps more seriously, the fact that you need to repeat this protocol many times to get a reasonable level of soundness has a huge impact on efficiency. Okay, so this is clearly a bad proof system as far as efficiency goes. Nobody would think of using this proof system, for anything, even for three-colorability. Okay. So when we aren't happy with something, a generic advice is try to find the right abstraction. Okay, so let's find the right abstraction for this proof system. So again, the first step in the abstraction was already taken. We can think of this commitment as an ideal primitive. But still, can we take out of this protocol a clean combinatorial object or a clean information-theoretic proof system? And the answer is yes. And this is what we refer to as, that's the simplest kind of a zero-knowledge PCP. We'll see other kinds later, but this is the first kind we will see in this talk. For those who know traditional PCPs, it's like a traditional PCP, except that it's also zero-knowledge. And I explain what this means. So syntactically, the prover here takes a statement X and a witness W, and in polynomial time converts them. Okay, it doesn't need to be polynomial time, but we will typically want honest parties to run in polynomial time. So the prover computes a proof pi. What is a pi? It's just a string over an alphabet. In this case, the alphabet size is 3 because this string will just be the sequence of colors. Okay, you take the nodes in some order and you just write the color of each node. Okay, so I don't talk about graphs, right? I just consider the coloring as a string. Now, the verifier in a zero-knowledge PCP tosses coins and picks a certain number. It doesn't even need to be a small number, but a certain number of symbols of the proof that the verifier chooses to read. Okay, and now we can make a very simple security definition. It's simpler than the traditional notions of zero-knowledge. It's information-theoretic. We can have completeness, typically perfect. The zero-knowledge here, it's public coins, so we can assume that the coins of the verifier are public. And zero-knowledge is perfect, okay, with respect to the honest verifier. So here we consider an honest verifier by default. So an honest verifier, no matter what coins it tosses, it doesn't learn any information about the witness, or more generally, you can perfectly simulate the verifier without knowing the witness. And finally, we have this soundness error parameter, epsilon, which we can generically amplify. In this model, it's very easy to amplify soundness, just repeat independently with different copies of the proof if you want to maintain zero knowledge. Okay, so this is a very clean proof system that generalizes, or you can think of it as an abstraction of the three-coloring proof system. And now, in this language, we can have very clean efficiency measures, right? We can talk about the alphabet size. We can count how many queries the verifier is making. And we can look at the prover computation and verifier computation in this clean model, right? There is no crypto going on. It's a very clean model. This is really, efficiency measurements are very clean and very algorithmic in nature and do not depend on all kinds of questions like what is the security parameter, what assumptions we're using, and so on. Right? We have very clean efficiency measures. We can start right away to ask questions, right? For instance, you know, how many queries do you need to make? What is the minimal expansion from the witness to the proof, and so on. So in this model, these efficiency questions are very clean. Let me just make some remark. In the literature, starting from the work of Kilian, Petrank, and Tardosh, the notion of zero-knowledge PCP often refers to a more difficult to implement version where we also need zero knowledge against a malicious verifier who can read a bigger number of symbols than the honest verifier. So typically, for instance, a typical setting is where the prover is given a parameter t, which is the threshold on the number of symbols that a malicious verifier can read, and the proof size is allowed to grow with t. But an honest verifier, we want him to run just to read only polylogarithmic many symbols or bits. Okay, so this is a typical setting of parameters that is considered in the more difficult to implement setting of zero-knowledge PCPs with malicious verifiers. And I should note that this is the first open question in this talk, that this is a work with Moore Weiss and Guang Yang, where we managed to get this type of malicious zero-knowledge PCPs with non-adaptive verifiers, but only with witness indistinguishability, which is a weaker requirement than zero knowledge. So the corresponding question that is still open is, can you design, regardless of efficiency, can you design a zero-knowledge PCP for NP with malicious verifier, where the honest verifier makes non-adaptive queries. So it doesn't need to do 2 rounds of queries, but just 1 round. In existing constructions of zero-knowledge PCPs that satisfy the zero-knowledge requirement, not witness indistinguishability, in all existing constructions, there are 2 rounds of access to the proof by an honest verifier. So that's a very clean open question in this space. Okay, so now we have this information-theoretic proof system. How do we compile it into a protocol we can run? So the first observation is that typically we cannot directly implement this zero-knowledge PCP, because how is the proof communicated to the verifier? If the entire proof is being communicated, then no zero knowledge. And if the verifier just asks the prover, hey, I want these symbols, what goes wrong? Soundness is lost, right? So soundness crucially relies on the independence of the proof of the queries of the verifier. Cool. So we have different kinds of compilers. This is the classical compiler of the GMW that uses a commitment scheme which is statistically binding and computationally hiding. And there is a more efficient version, constant round version. Another approach, if we want to get statistical zero-knowledge arguments, is to use a commitment scheme which is statistically hiding and computationally binding. And this is originated from Goldreich and Kahan, and you also have a constant round version. And these 2 compilers, these are very different compilers, their proofs are very different, and they both yield zero-knowledge proofs or arguments in the plain model with incomparable security features. If you're willing to make, and all these schemes are interactive, the most you can get here in this approach is a constant number of rounds. If you're willing to rely on this abstraction of a random oracle, right, to assume that you have a perfectly random function, then the Fiat-Shamir heuristic can give us non-interactive zero-knowledge arguments in the random oracle model. And that's yet another cryptographic compiler. So you have here 3 different cryptographic compilers that can take the same type of information-theoretic proof system and yield protocols that have different features. With constant soundness, it's easy. Good point. So with constant soundness, it's very easy. The challenge is to get constant round protocols with negligible soundness error, because parallel repetition does not work as expected. Okay, so we can even consider the goal of building, and there's a lot of work, including very recent one. This belongs to really to the theory side of building non-interactive zero-knowledge proofs under so this requires this common random or common reference string setup. But still, there are open questions about the assumptions from which we can get such proofs. For instance, a well-known open question is, can we get NIZK from the decisional Diffie-Hellman assumption or any discrete log type assumption? Recently, very recently, the question of NIZK from learning with errors has been settled. Okay, so this is still a work in progress that talks about replacing this random oracle by standard cryptographic assumptions. And this line of work can still use the same type of information-theoretic proof system, and only the cryptographic compiler, essentially only the cryptographic compiler is being changed. If you're willing to switch to a different kind of proof system, this is called NIZK in the hidden bits model. It's a very different information-theoretic proof system than this notion of zero-knowledge PCP. The classical construction of NIZK is cast in this model. So in this model, you can actually have a cryptographic compiler that is based on trapdoor permutations that can be instantiated from the factoring assumption. So here the cryptographic compiler is pretty easy, but actually the design of the proof system in this model is much more difficult and challenging. And in fact, we still don't understand the efficiency of proof systems in this model. It's much more challenging than this simple model of zero-knowledge PCP. So this is an example where I work much harder in the information-theoretic part, and then the cryptographic part becomes easier, though unfortunately, we only know how to instantiate this approach from factoring. Okay, so now, why aren't we happy with this specific construction? Or what are we trying to do next? We're trying to get much better parameters. And also, even though this construction is very simple and elegant, it is somewhat magical. It is magical in the sense that we have this non-trivial proof that three-coloring is NP-complete. And somehow, the structure of this specific language is so helpful, right? It seems really like we've been very lucky in getting zero-knowledge proofs. And somehow, whenever I see a nice trick, my initial reaction is that I'm happy, and then my second reaction is that I'm unhappy, because tricks are not kind of like mean that you're lucky that you found a trick, but things should be boring, right, if we understand them well. Usually things that initially look magical, they become more boring once we understand them well. So the goal is here to make these two a bit more boring, not when we present to others, but when we do our research. We want to understand things in a kind of less glorified way. But this is amazing, right? This coincidence between an NP-complete language and and the very simple and natural zero-knowledge proof. Okay, so I will conclude this hour with just a brief recap of things we heard about from Karmit yesterday. And this is the first kind of information-theoretic compiler I will mention in this talk. And this is really, I'm just kind of recapping things that Karmit said and giving some more examples of applications of this approach. So this is an approach that takes information-theoretic MPC protocols and uses them to construct zero-knowledge proofs, but it's convenient, especially in the context of this talk, to view them as information-theoretic compilers that take one information-theoretic object and convert them into an information-theoretic proof system that can later be compiled, say, using hash functions to zero-knowledge proofs. So, in particular, you can use this MPC in the head approach to get simple zero-knowledge proofs by making a black box use of very simple MPC protocols. So this is a protocol in the spirit of the BGW protocol that tolerates two corrupted parties. You saw from Manoj's sketch of this protocol. You have a different version of the compiler that Karmit, so Karmit showed in her talk a version where you commit to the views, the prover, so the symbols of the PCP are the views of the parties. So this is a very big alphabet, and the verifier reads two random symbols and checks the consistency between the corresponding views. This is the construction, the main construction that Karmit presented, cast in the language of zero-knowledge PCPs. So an MPC protocol effectively is the views of the parties defined as zero-knowledge PCP. You can also have a different version of the compiler where you have two types of symbols, a symbol that represents a view of a party, and another type of symbol represents transcript on a channel between a pair of parties. So if this is your proof, now you can randomly query a view of a party and an incident communication channel, and then it suffices for the MPC protocol to be secure against a single party. And in this setting, you can still use the BGW or BGW style protocols and only 3 parties. You can use, this is something that was mentioned by Karmit, you can use, and also Manoj described it a bit, you can use protocols that are based on oblivious transfer. Because you open 2 views, you can check consistency between the reported OT inputs and outputs in these 2 views. And something that Karmit again mentioned, there's been recent practical applications of such proof systems that are based on this information-theoretic compiler. And surprisingly, you know, it didn't stop at zero knowledge, but it continues to applications of zero knowledge, which is like even a classical primitive such as digital signatures. Today, at least one proposal has these MPC components running inside it. Yes? So you can do the whole analysis. Even in the paper, the ICOS paper, we only mentioned in the end that you can view it as zero-knowledge PCP. Zero-knowledge PCP is an abstraction. So you can view it, right, even the GMW protocol, yes, you can certainly view it as being implicitly based on zero-knowledge PCP, which is then compiled using a hash function to non-interactive zero-knowledge, yeah. Yeah. In a sense, this abstraction is kind of inherent, so you can find it in almost every zero-knowledge. With few exceptions, you can find a zero-knowledge, some kind of zero-knowledge PCP in every zero-knowledge proof system that's out there, almost without exception. Right. No. So this referred. So the LWE-based NIZK, it applies some version of Fiat Shamir in the plain model to a zero-knowledge protocol, which is a GMW-style zero-knowledge proof. So you can think of it abstractly as starting with an information-theoretic zero-knowledge PCP, then using crypto to build an interactive zero-knowledge, and then using a more refined crypto to make it non-interactive. So all of the second parts can be thought as part of the crypto compiler. So you can abstract this result and say, hey, I can compile any kind of zero-knowledge PCP that has certain properties into an LWE-based NIZK, right? You can abstract away. It's usually not done because the focus there is not on efficiency, or it's usually not done, but you can decouple the information-theoretic part from the cryptographic part, even in this result. So in this specific result, you want it to have a property that very few of the verifiers challenges can be. It's kind of like a Sigma protocol, except that Sigma protocol is a computational object. You can define an analogous property for zero. This is a distinctive feature of the Hamiltonicity-based ZK-PCP over the one based on 3 coloring, that you can have a version of the zero-knowledge PCP where almost all of the verifier's random coins lead the verifier to reject a false statement, with few exceptions. So this is a specific feature of the zero-knowledge PCP that is needed for this cryptographic compiler. But this is very unusual. Usually, almost all of the compilers are insensitive to this kind of properties of the zero-knowledge PCP. Okay, you can use a different kind of MPC protocols that are based on algebraic geometric codes, and you can use simplified versions to get zero-knowledge proof systems for circuits, for Boolean circuits, where the total proof size is just a constant multiple of the circuit size. Of course, we have much more succinct proof systems, but these are all arguments and not proofs. Okay, so for proofs, for general circuits, this is the best known. This is the state of the art. And one would expect that this is again something that Kermit mentioned, that circuit size will be a barrier in the context of MPC-based zero knowledge or zero knowledge PCPs. And there are two exceptions, right? There are two reasons why this is not really the case. First of all, and this is something that hasn't been explored a lot, but there is a huge literature on efficient MPC protocols for specific problems. For instance, linear algebra problems, right? So for linear algebra, you can have special purpose MPC protocols, say for multiplying two matrices. That's a simple example, where the computational complexity is asymptotically bigger, for all we know, than the size of the matrices, but the communication complexity of MPC is only roughly the size of the matrices. So you have a lot of literature. You have a literature on MPC over non-abelian groups, which can be very complex computationally, yet communication complexity of the MPC depends only on the number of group operations and not on the computational complexity of group operations. So this is specific tasks, some of which are very useful, for which even in the domain of MPC, we can break the circuit size barrier, even in information-theoretic MPC. I'm not even going to the domain of homomorphic encryption or homomorphic secret sharing. This is in the domain of information-theoretic MPC, where we usually don't expect to break the circuit size barrier. A second exception, and this is really what was a major part of Kermit's talk, is that this circuit size barrier only applies to the total amount of communication and not to the communication per party. So by setting up a good MPC protocol and let's say having square root circuit size many parties, you can have information theoretic protocols where the total communication is roughly the circuit size, but the communication per party is only roughly square root of the circuit size. And this is really the idea behind Ligero, that allows it to get all the way to square root the circuit size, okay? But square root circuit size is pretty much, for now, where these MPC techniques stop. And in the second hour, I will talk about different kinds of proof systems that allow us to go fully sublinear, to shrink communication much below square root the circuit size. Okay, thanks.